Thank you for joining us for this demonstration of a double pendulum, a famous dynamical system studied by both physicists and engineers. Known for being chaotic, meaning a small change in its initial value will lead to a large change in its response. You can find a lot of great examples where people have built these and shown their results on YouTube, showing just that. We today are going to show you how to simulate one in the Mobile Multibody Dynamics app. Begin by tapping the Create button. Give your model a name. And provide a description. Here we're going to talk about two rigid bodies connected by two revolute joints. And we're going to add gravity. We're going to use the uniform gravity method with a constant of 9.8 meters per second squared. Apply gravity in the -y direction. We're going to simulate for 10 seconds. And the rest of our settings can be left as their defaults. So now we've created just a blank model, and we're going to start by adding a revolute joint. We're going to use the defaults to begin with. Now to attach our model, we're going to add a rigid translation, and we're going to slightly offset this in the -x direction. This will connect to the back of our first pendulum link. Open our Bodies menu and add a rigid body box, which we're going to attach at the point that we just created at the back of the rigid translation and to the frame we defined by the revolute joint. We're going to give it density of 2700, equivalent to aluminum. Create a length of 0.6 meters, width of 0.2 meters, and a height of 0.02 meters or 2 centimeters. We're going to attach to the aft end and give it a color. We'll make it light blue. Moving back to our diagram view, we can see the first link being created. Zoom in a few times, and now we'll simulate pretty basic pendulum behavior. You can see it oscillating back and forth, a little bit jerky because we didn't create a very tight tolerance on the simulation, but nevertheless, that's not what we're interested in. We want to define our second pendulum link where most of the action happens. So we're going to add a second rigid translation. This will connect to the center of rotation for the second pendulum link. Another rigid translation we'll create here just for visual effect. We're going to slightly offset the point of rotation in the Z direction just to make the bodies slightly offset from each other, make it look a little bit visually more realistic. And we will create a second revolute joint. Once again, we're going to keep this with most of its defaults, but we're going to define it relative to our first joint. Another rigid translation to slightly offset the second link from the point of rotation. And finally, we will go into our Bodies menu to create the second link. Very similar to the first link that we created to start this model. Here we're going to use the created reference point F, which is the point that was offset aft or back of the center of rotation, and we're going to use the second created frame, which is denoted E, and the remaining parameters we're going to set to be mostly identical to the first link, although we will give this one an orange color. Turning to the diagram, we will now let this model simulate, and shortly here we will see the full double pendulum system with both links. Rotate around a little bit and start the simulation. With both links starting at the horizontal, we see pretty standard pendulum motion, nothing too crazy going on. We'll look at the plots of the states over time, and we see actually repeated motion, so pretty orderly at this point. However, the next thing that we will do is we will demonstrate the change in that result as we slightly vary the inputs to the or the initial conditions of the model. So going into our first revolute joint, initially this one was horizontal. We're going to set its initial value to 0.1 radians. And we can see it's slightly increased in its initial angle, but largely a very similar response to what we saw before. So next, once again, we will look at the plots, and then following on from just reviewing this data, what we're going to do is do one slight uptick in the initial value again, going to the same revolute joint, where before we set its initial angle to 0.1, we're going to set it now to just 0.2. Again, at the diagram, we're going to simulate and shortly see the model. Again, a slightly larger angle. Once again, fairly orderly and repeated motion, although we can see just at the very end, we start to get the second link flipping over. We'll watch once again. So what initially seemed like a very similar response with just the 0.1 radian initial difference in angle, we can see a substantially different response with the flipping over top motion at the end. Now, just to continue on with this video, we're going to do a couple more variations. So now going through a value of 0.3 radians. This time, and as you might expect, as we increase the angle, we're going to see even more chaotic looking response, more loops, generally a more unpredictable response, although by the system of equations that we simulate, it's of course completely deterministic and dependent on the initial values. Finally, we will close out by doing one more iteration on this model, going to a value of 0.4 radians for its initial angle. We will simulate this, and much as you might expect, as we keep upping and upping the initial angle, we keep getting a more and more disorderly, chaotic looking response. A lot of loops, a lot harder to predict where exactly that bottom or yellow link is going to end up. So now let's move on to the real nerdy stuff, starting with the plots. So interestingly, in the generalized speed plots, we can see the more chaotic motion not repeated from cycle to cycle. Here are our equations of motion, somewhat long, albeit I'll admit partially because of the way that we define this model. If we look at our bodies tab, we can see the equations and values for the masses and moments of inertia. If we look at our points tab, we can see the positions, velocities, and accelerations of each of the points that we define in our model using our revolute joints and rigid translations. The frames tab, we can see the direction cosine matrices, and on the symbols tab, we can see our constants and degrees of freedom. So that concludes our demonstration of the double pendulum model. We hope you find this interesting and that you will try the app and create one of your own.